IMS 2024 in Washington, D.C. I'm Martin Rowe with the eWorld, and we are in the Keysight booth, and Tali Amir is going to tell us about IQ data characterization. So, Tali, why don't you tell us about this demonstration you have here?
Sure, yeah, so what we're doing is homodyne system characterization. Basically, it's an zero intermediate frequency transmitter or receiver. What we're doing is we're using the IQ baseband outputs of the VXGC to send a signal through a customer device under test. It's one of our telecommunications partners. What it's going to do is it's going to do IQ mixing, upconvert our IQ baseband signals to a center frequency of 72 gigahertz, and then send that through the V3050A, which is our frequency extender, and transmit that RF signal into our UXA, which is our spectrum analyzer. What we're doing is we're sending a calibration comb. So it's a calibration signal that's going to measure the channel frequency response of the system. And it's going to characterize the IQ imbalances of that system. So things like time skew, quadrature phase error, and gain imbalance. This is our measured response of this particular system at 72 gigahertz frequency and 1.5 gigahertz bandwidth. So what we can do from here is we can actually take the channel frequency response and we can pre-distort any signal of our choosing. So what I have here is an example signal, a modulation wave, sampled at 1.92 gigahertz sample frequency. And I'm going to save that to another file. And I'm going to just click pre-distort. It's going to use our channel frequency response to pre-distort the signal. Once that's done, what I can do is I can view, I can try and demodulate both of these signals using VSA. What I'm going to do first is I'm actually going to pre-distort our calibration comb so that you can see just how good of a job it does in correcting for the IQ imbalances of the system. So what we expect to see here is a decrease in the magnitude of the images in our system. As you can see, our unbalanced tones are completely eliminated. They're reduced down to the noise floor. You can't even see them anymore in the scaling that we're using in VSA. The balanced tones are completely equalized. We can see that our calibration comb has a completely flattened balanced tone response and virtually no images. We get about 40 dB of dynamic range. So what I'm going to do now is show you what our pre-distorted modulated signal looks like.
Okay.
Going into IQ Tools, it's just a tool that we use to download arbitrary waveforms. And what you can see here as we're demodulating is we have a 16 QAM signal at 1.5 gigahertz bandwidth. When demodulating in VSA, we can see that we get an EVM of about 5.3%. Pretty good. Our quadrature error is on the order of about 5 degrees. Gain imbalance is about 0.2. But from our pre-distorted signal that we have saved here, we can see that it reduces the EVM to about 2.3%. Quadrature error is on the order of milladegrees now, almost completely eliminated the gain imbalance. So we're eliminating a lot of the IQ imbalances of our system in a frequency-dependent manner, basically automatically using our VSA correction procedure.
Very good, thank you.
Yeah, thank you.